Welcome. Once again, this is Lita Downs from the Office of Teaching and Learning Excellence, and I would like to welcome you to today's session, Statistical Techniques to Improve U.S. Estimators' Unreliable Data Problem. This series is part of the CMHP Virtual Symposium, and today's presenter is Dr. Tomeka Williams. It's so great to have you, Dr. Williams. I know you are affiliated with the PhD Management Program here at Walden, and at this point, I'm going to turn it over to you. Welcome, Dr. Williams.
Well, thank you. Thank you very much, Linda, for that. I definitely appreciate you making sure that everybody's all set up. Well, welcome everyone, as already mentioned. Basically, I'm here to present to you some work that I've done at Walden as a PhD student, as a part of my dissertation research, and then I've been continuing it in different areas. But I'll kind of give you that background. Go ahead and go to the next slide, please. And so just to, give you kind of set the stage, I've been working in something called, or at least my career field, been doing it for about 20 plus years, as cost estimation, or being a cost estimator, also known as a cost engineer, also known as an engineering economist. But effectively, that career field is one in the federal government space in which, you're given the hard problems of, how much will it cost, over a 40-year life cycle to build the next generation aircraft warfighter, like Joint Strike Fighter, or how much will it cost to build the next hypersonic missile, and doing that, with Space Force or Missile Defense Agency or anything like that. And so over the years, I've been a cost estimator, like I said before, for about 23 years. My first duty station was LA Air Force Base, where I did Titan missile rockets. The continuous problem that always seems to come to bear is, do I have enough data, or where am I going to get the data from to basically determine, how much should I pay, for the avionics piece, and, for this year. And then, let's say if I took inflation or added inflation logic on it, going 40 years out, you come up with that larger estimate of what you're going to spend on R&D, what you might spend on procurement costs, what you might spend on operations and maintenance. And so that's the world of a cost estimator. And so, my study at Walden kind of started with, let me start with the career field, and better understand, is there something out there that can truly help us, or at least help the cost estimator when they're actually sitting down doing a cost estimate? If they run into problems with data, is there something hands-on that they can do? And so effectively the specific management problem that, that I realized after going through the literature, looking at a lot of policy documents and expectations of cost estimators and cost engineers, is that there is a lack of research when it comes to, are there any techniques to handle the unreliable and incomplete data problem when you're a part of the US cost estimation discipline? And so where a lot of my literature took me between the years of, I think it was roughly 1995 to 2021, kind of that's the big broad range. Like cost estimating wasn't a career field probably until the 90s. And a lot of our cost estimators, they're trained through corporate universities. So it's not like you can go to Walden or University of Virginia or Virginia Tech or even Stanford to say, hey, I want to be a cost estimator. And, let me see your curriculum. And so I had to start with, looking at how are cost estimators trained, and what does the literature even say about, how should they handle missing data? And so going through all of that, what was discovered effectively was like the certification warehouse, like US Code 2334, tells us effectively, like, cost estimators should have data, and they this is how they should operate, and they must always have reliable and complete data to build their estimates from, was a consistent theme. But there was nothing in the training or in the universities that said, okay, well, what do you do when you don't have data? Or if you might have data that, it doesn't behave right when you put it in, and when you plot it into a scatter plot and you're doing linear regression and things of that sort. And so that's kind of where all the literature, all the documents tend to side with hey, there's really nothing formal that says how to handle the missing data problem for cost estimators. And so ultimately, I set out in the research, I wanted a quantitative study, but the best way to measure it, not only that I wanted it, but was to basically, let me do a real experiment or get as close to an experiment that I could to actually test and measure what are some ways that other disciplines, handle their missing data problem. And let me bring some of those into the cost estimation world and engineering economics world and see how well how well will it render being able to give me the same number or give me a good value. And so thus I ended up testing and measuring the level of what I'm calling predictive accuracy of missing data theory techniques that I saw in the literature, apply them to the cost estimation problem for defense cost estimators, and just kind of make a determination of what techniques render the data sets, being able to make them more complete and more accurate. And so, it was an interesting journey, but effectively, some of you might be wondering like, hey, I've heard of missing data in my studies, or, I've seen in SPSS that, there's are ways that you can do this. Why is this so different? Well, like I said before, in the cost estimation world, none of the training spoke to it. All of the training either said, even when the problem was addressed, the recommendation would be go out and get more data, or, go talk to Lockheed Martin, if you will, and just, just make them give you the data. But a lot of times in life, that just doesn't happen when you have an estimate due in 2 weeks, or you have something due in a month. And, they're trying to get contracts out to get this work done. And so the significance, obviously, of this study was, it was important simply because reliable and comprehensive data, cost data, is an essential part to having credible cost estimates. And it's not only, just in because people think it's a good idea, but it is in policy, statutes, and regulations. So a lot of the laws actually, speak to it, as mentioned before. But even, some of my other sources, Dr. Marin at the time, he was the Office of the Secretary of Defense Cost Analysis and Program Evaluation appointee. And, he even said, he even brought this to light that, yes, we have a problem with credible data. I guess the other way to also bring this home for a lot of you, I think everybody knows, DOD might get it wrong. They might spend more than they should. Software overrun costs tend to happen quite a bit. I think if anybody ever remembers the story about the hammer, I guess the $200,000 hammer cost, people can get things wrong with these estimates. And so the significance is we want to get better at it. And we want to make sure that we're using techniques that, that potentially other disciplines use that we're not using, but also we want to take advantage of the computing power that some of the systems have that we may not use. When I talked about other disciplines using it, think of, clinical trials when you're looking at pharmaceutical drugs, or if they're doing, very large longitudinal studies, missing data happens. Unfortunately, you might have people that fall ill in a study, or even some of the, if you're dealing with human beings, some may perish and they're not able to complete the study. So some of the techniques that I used in my research were borrowed from those places. But like Little and Rubin, is a critical component theorist who actually talked about missing data theories, way back in as early as like in the 1970s. And, missing data is such a big problem today that they even redid their theory in their book in 2021. So that's, showing that it's a significant problem. And so, back to them, that theoretical framework, my study was totally grounded in missing data theory and just all the techniques that you could think about in terms of how to handle them. And so, some of the approaches, the complete case analysis technique is common. And, they have, various versions of those, such as listwise delete, or even, various direct imputation methods. but there are also, some other techniques out there that, are beyond the scope of the study that I did at Walden, but I've been advancing, since in terms of using, bringing in machine learning algorithms and just basically seeing, how well do they fare with being able to basically give you complete data sets because you might have values that are missing. Next slide, please. And so the relevant scholarship, like I said, I went through, I worked on my dissertation for roughly 5 years at Walden. So Walden got their fair share out of me. But it was very good because I think it was a timely topic. And when I started the research, data and the missing data problem and data science hadn't really taken off just yet. But, I started with public policy effectively to basically look at that to see, what was it saying about, what was the, what were the expectation for cost estimates and cost engineers in their products. And basically, the upshot there was that there was, it requires data reliability and completeness. And by law, you shouldn't be using incomplete data or data that's faulty. That would basically give you, inappropriate outcomes or fictiously say, this should cost you $7 billion when you had no basis of estimate around that. Kind of going to bullet number 2, I then began to look at the effect of that public policy on, cost estimates and the data reliability completeness area. And, just realize that it wasn't getting done, thus, being able to cite various examples in which cost overruns have robbed, Department of Defense efforts, from ships to IT systems, to aircraft like the Joint Strike Fighter and things of that sort. And then effectively the gap here is, why are we always relying on, kind of the corporations to kind of give us the data? Like, what's the mathematical solution? Is there something out there that we should be using to kind of expand those options to handle a cost estimator's unreliable and incomplete data problem? Obviously statistics, that's forecasting for us. You can also, use, more advanced statistics, to get there, such as artificial neural networks and things of that sort. And so it was like opening up the aperture for looking at, various different options. But basically that was how I was able to pull everything in. And then obviously looking at just how have other disciplines handled it. Like a lot of disciplines, like I said, they deal with the human being as your independent variable, if you will, not necessarily a data set being your independent variable. And so that was the kind of the uniqueness of this study, is that the data or the subjects, instead of a human subjects, it's, element number this out of the software line of code, like, what's that number? I'm going to take that subject, remove it from the data set, create an artificial missing data problem, and then use all the statistical techniques that I chose to try to fill in the holes. And then effectively, let's see how well that imputation could fulfill that missing data problem. Like, how close could it get to being as accurate as the known, or what I call the predicted, the original data value. And so ultimately, the last point in my how I structured the scholarship was asking the research question of, could missing data theory truly improve data reliability and completeness for the data that I used in my study? And so effectively, the statistical method that was used to perform this pre-experimental design, it was a one-group pre-test, post-test design. When you look in the literature, it's such a interesting way to actually even discover how to structure this well. Like pre-test and post-test is, Campbell and Singleton, talked about this quite a bit. But like I said, when it comes to actually using it for data purposes, nobody's really, when you look at how to structure the experiments, it took a little time for me to basically get through my methodologist, but then I was able to bring them along, and it's like, okay, no, you're right. And so kind of walking through the diagram here, the statistical method approach, like I said, it's very simple in nature, like once you're around it long enough. But what I set up for this pre-experimental design was I took in the original data set. So I had, I started with, I pulled in corporate data from a corporate university that's It's representative of a cost data set that would be used for building basically a system of, and I'll go ahead and read, but like software application types that were kind of control and signal processing type of data. It was data that was for an air vehicle in the operational environment. And the data set, it was not an agile methodology, it was a waterfall methodology, but simply because of just normalized data, the best normalized data that I can concatenate with the data set that I was allowed to use from the IRB. But basically, I took that original data set, I stratified it in various ways and coded it, but effectively, like I had roughly a total of 50 programs that I started with initially. I ended up cutting it down based on the normalization to roughly 30 of them. So ironically, that worked perfectly in terms of statistical significance. But the data set type was, the independent variable. So whether it was eSLOC data or final SLOC data or software interface data. So that's how I named my data sets. And then in each of the data sets, if it all came from the same data set, if it came from the same data set, so let's say all of these are eSLOC, estimated software lines of codes. My second variable was, what's the various percentage of missing data that I would take to that data set? And so in my case, I did simply 8 different levels of missingness. And so like 5% of the data was missing. In this one, 10%, 15%. And I did it all the way up to in increments of 5%, but all the way up to 40%. And I went to 40% simply because all the literature tells us you can't exceed, like you can't go beyond 40% of missing data or using the missing data theory techniques because it just doesn't work. And so anyway, so basically, my independent variables were the categories of data sets used, the levels of missingness percentages, and then the technique used. And in my study, I ended up having 3 techniques for the dissertation, but I think in practice now I've done more. Like even like of a roughly 6 data set types that have algorithms and other cool things to basically see how the data performs. And so basically it's that original data, you apply the missingness, you apply the technique, and then you come out to determine, okay, what's that missing data percentage? What's that predicted value? And how close does that predicted numerical value relate to that original? And so that's effectively what I studied. And how I measured this in terms of the dependent variables was simply what's the absolute value difference, so the absolute error. So it's just the subtraction of, what the original data item might have been and what was predicted, you subtract the 2. So A minus B would give you that absolute error. And then that representation as a percentage is simply the relative error. So that was how I set up the experiments to go through. So next slide, please. And so even digging deeper just into this, so the research question, as I set it up for this study, was to what degree, so it was a degree question, which was, to what degree can missing data theory techniques accurately solve cost estimators and engineering managers' unreliable and incomplete data problem when data values are missing from a representative U.S. defense cost estimating data matrix? And so you might say, once again, why representative? Because a lot of the data, if I was showing this, like in the workplace, you have to have NDAs or it's proprietary data. It's like the secret sauce of what makes, Raytheon's, sensor, does what it, you can see in geo orbit or whatever. So I didn't want to, obviously for a study that I would want to share, I wanted to have, more representative data that wasn't proprietary. And so hence making sure that the research question was structured around that. And so, going to the bottom here, like the procedures. So there are other different tools that can be used, but for the purposes of the dissertation and keeping it simple and making sure we can get through, I use simply SPSS, IBM SPSS 25. I think everyone at Walden does have the access to that. And there's different value, or there's different modules within IBM SPSS, but there is a missing value analysis section that you can turn on that, can help you calculate easily. Well, I shouldn't say easily, but it helps pull, if you have large data sets that you're pulling in, it can do it a lot faster than my hand can do it in creating kind of the using multiple imputation techniques, using linear regression. And so that's where I use that statistical package for that one. Obviously, listwise delete is very simple to do. Listwise delete is nothing more than basically removing data values or making the decision to drop data values. And so I could do that in Excel, and obviously simple imputation techniques such as just determining what's the mean of the rest of the data set could easily be done. But also, just as a side note, not for the dissertation, but other statistical techniques that you can get out of missing value analysis, you have the expectation maximization algorithm, which is an algorithm that is a part of the machine learning family, and you can use that as a potential imputation technique. And there are a couple of others that are there, but in any case, that was basically how I handled it. And depending on how many data sets that I could get whole, this could easily have been a 3-way repeated measures ANOVA. If I'm doing the whole thing, it could be a 4-way repeated measures ANOVA. But based off of what ended up happening with my data, I ended up having only a 2-way repeated measure ANOVA once the experiments had been done, simply because we realized that with all the data, the listwise delete technique just wasn't a feasible option to be able to basically impute data, for this study and for the for a cost estimator, simply because it wouldn't help you, it was a null value effectively. And so back to the participants and secondary data concept here that was used. Like I said, it's not people, but I'm humanizing, or I'm making data a human. So I was able to obtain synthetic data from a non-proprietary U.S. cost estimation data repository. I say a corporate university here, but the great folks at Defense Acquisition University were very helpful, and as well as some of their work that they use for courses, use something called the CADE database. And then they had created effectively something that they called the FACADE database, which was they kind of jumbled the numbers and so that way you could anonymize the different program of records, if you will, and initiatives. But effectively, that's what I was able to use. And I was able to get about 20, well, actually, I was able to get 28 different types of software effort data from them. And so basically, it was 30 out of the 55 of the programs that I actually ended up using for the study. Yeah, they gave me 55. And then when I told you about the data set matrix, the matrix had, in terms of type of software effort, characteristics, I had roughly, I think it was total of 28. And if not, I have it here if I'm pulling them, missing them up a little bit. But the upshot is, I had a wide variety of software effort data to use to basically play with statistical techniques to see how well imputation or missing data theory could work. And like I said, these programs, like they were used in a case study for one of the courses that the university uses to teach how to do software cost estimation. And so at the end of the day, I was able to analyze, or basically conduct 4,704 pre-experimental treatments, in which I then applied the kind of the one group pre-test, post-test, no control group pre-experimental design. So I have to put that all there. And like I said, it was it was interesting, like I said, just based off of my study design and how it was created. But it's all grounded in the literature. And so basically, all the numerical values that I did generate were all, ratio scale measurements. So that way I could do absolute error and relative error calculations using the approximation error terms. And I was able to measure the predictive accuracy of each of these applications and what I'm calling the traditional missing data theory, because the machine learning ones are obviously, much more. So the findings. So out of my 28 data sets, in which used 30 synthetic and analogous 30 software programs. Basically, I was able to, make a determination of, how well or to what degree could missing data theory solve the problem. And so out of those experiments, there were 1,568 trials that actually ended up getting conducted for each of the missing data theory techniques. So thus I had 3 missing data theory techniques: listwise delete, simple mutation mean, and multiple imputation linear regression. And so as you can see, kind of the main exciting part of this was, how close can I get within that original value? So looking at that top right table, we were able to get, or at least me and my data, we together, we were able to get between 0.1% and 20% of the original value for simple imputation means 16.4% of the time. And when I'm using the linear regression technique, roughly 18.4% of the time. And so that was, it shows promise. Now, obviously we want to be you can be within 80% of the original value, but that's kind of far. And so, we want to, ideally, how well can we get some value out of missing data theory? So it's something, not saying that it's perfect or it's an end all solution, but if you have absolutely nothing to impute your data or you have no techniques, it does give you promise, or at least this pre-experimental design for this specific data set that was representative for software cost estimates, 30 programs, 28 different types of software effort data, it fared pretty well. I guess the other thing the bottom line here is, remember, I'm answering the question, to what degree can all of these techniques empirically, come closest to the ground truth or the original numerical value? Like I said, and that was the big finding or the big takeaway. The other thing is I wanted to test for as a part of my research question is, what's the interaction between the dependent variable as well as the independent variables in terms of, is there a relationship happening? And so how you basically test for that is you look at your estimated marginal means chart to kind of give you that sense of, if the means are not equal for the dependent variable and each of the independent variables, in this case being the missing data theory techniques, basically, you can determine that there's no interaction occurring between those 2 dependent variables. And so, and basically that would be noted if the lines actually cross between the red and the blue. So next slide there. So another finding, so this is kind of a bonus, but so after the dissertation, I think I did a conference earlier this year, the International Cost Estimating Association Analysis Conference. And this is kind of where all the certified cost estimators go. And I had the opportunity to present. I think I ended up having roughly 70 folks come in. So it was actually one of the largest sessions because, we're looking for, is there something new to help us? And so I just took a live poll there just to get a sense of, is this relevant or not? And, have you ever conducted software cost estimates with data input variables that were missing? And so, I can have, 43%, of my folks or at least 43 out of the 81, let me not lie, out of the 61 said yes. And then I just asked, how do you typically handle the problem? And so you can see, we have some other areas there. Multi-echelon predictive regressions as approach. Some people are saying use analogous data and historical data, but my point of my study is, what if that historical data doesn't exist or you don't have any analogs to go to, like you've exhausted the possibility? So what can you do other than say, I'm sorry, I can't give you an estimate, which is unacceptable. So in any case, but just gives you some ideas of what some people were thinking. Luckily, I think I asked my question throughout the conference. So my poll continued. So I think in my session, I didn't have a lot, or at least I didn't have as many, responses, but over time, I did see like some people say, yeah, we are trying to use some of the imputation techniques. But also like Kokomo too, like they'll just, use whatever the parametric model has to say. But once again, I say the parametric, you have to give it input variables. So if you don't have data to put into the Kokomo model, it's really, it's garbage in, garbage out. So you do need data. But you see here, some people just say we dropped the missing observations. So, from this not being a study before in my career field, like there were no papers on it, that I was able to find in the literature, over, like I said, I really went from 1990, well, I said 1995, but truly as far back as 1970, I think, yeah, 1970 all the way up to 2021. But, in terms of, just seeing the relevance, like this definitely, my work does definitely contribute to the career field. And it actually is kind of the first scholarly piece that tries to pull it up to the forefront for us to now continue on doing more advanced techniques to bring it into play. I'll also note, like recently I also did a conference in Bangalore, India, but I did it remotely, but it's another kind of a management and data analytics conference in which they saw the relevance and basically, it's seeing what other techniques could be used to improve this. So next slide, please. And so overall, like, interpretation, the best thing that came out of it was, okay, there is some degree of improvement that it can get pretty close to predicting or forecasting, data that's not there. And so, I guess, the bottom line, I think depending on how I splice the data, SI or simple imputation mean had the strongest level of predictive accuracy when I looked at it at the data set level. And so that was interesting to see. But I think when I looked at it at other levels, if you only cared about kind of honing in a little bit deeper, you had better closeness with the linear regression technique. So kind of the bottom line is that, depending on, your situation, this is basically something that you can do, in the comforts of your home. You can pull out the calculator, you can pull out, whatever your missing data theory technique of choice is, and you can start imputing data into your data sets if you have blank values or values that you don't think are reliable or complete enough for you to complete an analysis. And so obviously the limitation of the study was that, the instrumentation that I used to do predictive accuracy was limited to IBM SPSS. Like I said, there are more tools out there that are more advanced, but they're costly and they take the, but in any case, if you're in a homegrown environment and on a budget, SPSS, Stata, those are all good tools to use. The other, just in the future, one of the tools that I'm using now is called the WECA tool. It's out of the University of Australia, in which is a machine learning basically tool set that helps you can impute missing data with it. But also limitations to the study that I did here at Walden, not having a control group for the one group pre-test, post-test, pre-experimental design it's a weakness in general, like if you're looking at a one group pre-test, post-test, but remember, there is no control group because I want to be flexible with the data. Like, I don't, it's not data doesn't have feeling. It doesn't have a good day or bad day like a human being. They're not biased. Data is, just data, or at least that's how I see it. But in any case, but I did want to say that as a limitation because that is, what they do. Like they like to see more so control groups when you're dealing with pre-test and post-test. Perfect example, if you had a group of smokers and non-smokers and you were doing an experiment on them, you would want to have a control group to compare those results to. So it makes sense, but just when you're using data as your human being subject, it's a little different. So maybe perhaps I need to rewrite the one group pre-test, post-test design for data. But in any case, but the recommendation, research, this research and, it's as a quantitative study, it was able to give a perspective on and address a problem that, obviously since 1972 hadn't been discussed. And I didn't talk about this, but the 1972 document was a government accounting office GAO report back as far back as 1972, had basically said, missing data is a problem, or, not having data for estimates is a grave problem. And GAO has since created guides in 2009, as well as, ironically, in the year 2020, that even talked to, they still had a problem. And so this is taking the problem set into a person's hands and just giving you a hands-on approach to solving it, instead of just, depending on, something else, like such as policy, because I think that's what also I had noted in the literature, is that a lot of studies, or like anything that was closely remote to being, like a solution, is let's change the policy and make them report to us their data better, or let's, put it in the contract language, or let's pay more for the money, pay more for the data, but nothing about, how do you solve it if all of those things fail? So the societal change implication is simply, this study provides an opportunity for societal change, in helping not only cost estimators, but engineering economists when they're dealing with data sets, engineering managers, and even other folks that just, if you have to deal with data or a data repository, this is something that you can, that's beneficial for them, because, three things: it helps improve data incompleteness. It helps them predict, or help create better estimate predictions, simply because you do have, better data, or you've been able to impute what we expect to be better data. And then ultimately, if you have better data and your forecasts are more accurate, you're funding activities at the right level versus overspending or even underspending. And so ultimately reducing taxpayer funds that are spent on defense acquisition cost overruns is basically what we were going after in terms of improving societal change. So next slide, please. So I think that gets me, I'm sure, to all my references. So you could go through these, but just high level, GAO, I mentioned them, like, as you can see, the 1972 up to 2020. Some of the theorists, such as Graham, who wrote some of the books, the ICEA organization. Like I said, I ended up going to that conference, but they even have a certification exam in which how to handle missing data is in a topic. So just pointing that out. The other one, I like the second one, the Joint Agency Cost Estimating Relationship Development Handbook. That was very instrumental, or just another key thing for me, when it basically it said, we know that missing data is a problem, but the how to solve it, just go ask for the data. And this is an authoritative, handbook on how to do cost. So just not helpful. And then obviously my favorites, Little and Rubin, as far back as 87, 2002, even 2020, like I said, they came back out. And even as you can see there, Rubin back in 1976, he was even talking about inferences in missing data before he teamed up with Little. So any case, and more, obviously, and then I think I give credit to So, Yoon, and Bae, just in opening my eyes that, or at least in the literature, software was talked about in software efforts. So I'm like, okay, I can easily add to the language, or the scholarly language, when it comes to software effort estimation. So with that, that concludes my talk. I think we have about 5 minutes for questions. So sorry if I went long. I think I did see some things happening in the chat. So happy to answer your questions.
Wonderful. If you have any questions, or if you want to unmute yourself, you can certainly do so. We have a few in the room, so please feel free to either type them in the chat or unmute yourself. So I have a question myself as I'm listening in awe to all of your fabulous work. So what inspired you to get into this? It's really very impressive, simply put.
Well, thank you. So what even started my love? I mean, so I go back, probably, I'm the kid, I was in a program when I was in 4th grade called International Children's University, and they taught us like trigonometry. I learned coding, programming way back when. And I've always loved numbers, and I'm not afraid of a spreadsheet. I'm not as afraid of data, and I've always loved it. And so, but what I like about the cost estimation world and the engineering, when you tailor it and you pull in the economics world, to me, it's the engine of society. I mean, like you can't buy anything without understanding, or you shouldn't buy anything, without understanding its cost, its makeup. Um, and then obviously when you have that data, like seeing it over and over again, it's like, okay, sometimes you might know maybe what this should be, but we should use math, use statistics, use the tools that, there's a lot of computing power now. Like, it's no need to waste it. And so anyway, so my, just the love affair of just wanting to try to forecast or predict the next big thing. Like, I love stocks too. So, and Bitcoin,
That's
crypto.
wonderful.
But yeah, I mean, yeah, I'm not too thrilled, but we see where that's going. But in any case, it's to me just the art of statistics and the art of math. Like, I challenge anybody not to be afraid of it. Once you get into it, you'll start seeing it. It logically just starts, coming together, and you want to solve its problem. So
Fantastic. Well, your passion is definitely very evident. So, oh,
good.
any else? We have we just have a minute and a half left. Any other final questions or comments?
And don't be shy. Obviously, if you don't want to answer them, ask them here. I'm sure there's probably an opportunity to reach out to me, especially if any of you are still students at Walden. Happy to answer any questions, especially if you're still thinking through your research and kind of how to pull the concepts together. So, any questions in terms of that?
And Dr. Williams, if you don't mind entering your email in the chat, your Walden email, that would be fantastic, in case we have folks who are listening to the recording that may want to reach out with a question or a comment. I greatly appreciate that.
Perfect.
And while you're typing that in, I want to thank you for presenting today. I know it took a lot of preparation on your part, and we really appreciate it. I appreciate those who are in the room listening and those who are listening to the recording. For you too are increasing your professional development and awareness in these very important topics.
Okay.
We have a few sessions coming up, but I do want to say that this particular session, as those of you who are listening to the recording will know, because you're listening, are being placed on the website, on the event website. However, if you missed a session earlier, it will be placed there. We just have so many great ones that are concurrently running. So do check back and also check and see what is coming up. I do want to thank you, Dr. Williams, once again for carving out time and for presenting today.